Hello, I am Melissa Ignaco, and I will be presenting on a linear regression model I built to predict melanoma tumor size. Melanoma is a type of skin cancer primarily caused by UV light that arises from melanocytes, which are the cells that provide pigment for your skin. It is the most dangerous type of skin cancer and can become lethal in its malignant form. Melanoma tumors can come in a variety of shapes, sizes, and colors, so it may be difficult to provide a complete set of warning signs. But tumor size is an important factor for the diagnosis and prognosis of skin cancer, and predicting tumor size can help physicians gain a better idea of whether the tumor has the potential to grow and thus become malignant. A research question that has been raised is how can different tumor attributes be used to predict melanoma tumor size? To answer this question, I used a training dataset from the Machine Hack Hackathon that focused on this problem. Winners of this hackathon used machine learning methods such as feature engineering and ensemble learning to approach the problem. My specific research questions for this project include: do all predictors have a positive impact on the response variable, and what is the best subset of predictors for predicting melanoma tumor size? The second question can be done by performing a hypothesis test between the full model and the model provided by the best subset algorithm. The third question is, does the final model still violate any of the linear regression model assumptions? Hypothesis testing can be done in terms of testing for constant variances and normality. And lastly, which tumor attributes have the most significant impact on predicting melanoma tumor size? From the dataset, I chose 5 predictor variables, which are shown in blue. These included the mass and size of area under study for the tumor, the ratio of normal to malign surface, unrecoverable area of skin damage, and the ratio of damaged area to total spread of the tumor. And the response variable shown in red is tumor size. All variables were continuous. However, no units were provided in the dataset, and the ranges for each variable are shown on the slide. The original dataset had a size of 9,146 data points, but I cut this down to have a sample size of 300 and used the first 300 points of the dataset for simplicity. I found this to be a sufficient sample size because a smaller sample size still followed the general pattern for the distribution of points as a full dataset. The original dataset also had 9 predictors, but I wanted to focus on predictors pertaining to the actual physical attributes of the tumor area. Some predictors seem to be more of calculations based on the physical attributes, which included standard deviation and error in malign skin measurement and penalty applied due to measurement error in lab, so these predictors were excluded. One physical attribute I did not include, though, was total area exposed to tumor due to high correlation with the other variables. Now I will discuss the preliminary analysis of the data and first-order MLR model. Based on the scatter plots among the predictors and response variable, it can be observed that many of the predictors are linearly related, indicating high correlation between the variables. The correlation plot on the right shows which predictors are most correlated. X1 is highly correlated with X2, X4, and X5, and X4 and X5 are also highly correlated, as shown by their correlation values below. X2 also appears to be moderately correlated with X4 and X5. Thus, I can expect there to be an issue of multicollinearity in my model. Some predictors also had a couple outliers, as shown from the box plots on the slide. X5, or the damaged ratio, was the only predictor without outliers. However, the outliers were not removed prior to creating the model because it isn't certain that these outliers will be influential cases. This will be assessed later on in the presentation. From the residual plot showing the relationship between the fitted values and the residuals of the MLR model, it appears that the residuals follow a negative linear pattern. The histogram for the residuals also shows that the residual errors are slightly skewed to the left. Thus, other potential problems that may arise are non-normality and non-constant variances. I will now move on to my model building and diagnostics process. According to my diagnosis of the first-order model, it appears that a relatively low proportion of the response variable can be explained by the MLR model, as indicated by the low coefficient of determination value of 0.26 and the adjusted R-squared of 0.25. However, the added variable plots shown on the right indicate that a linear term for all predictor variables may be a helpful addition to the MLR model already containing the other predictors due to having sloped linear lines on the AV plots. In terms of other violations, the Brown-Forsyth test for constant variance and Shapiro-Wilk test for normality show that the model violates these two assumptions due to having p-values less than 0.05. There is also a major issue of multicollinearity among the variables, as the variance inflation factors for all predictors except x3 and x5 have a value greater than 10. Based on the influential plot of the model, there does appear to be some potential influential cases, but the suggested influential points have little to no impact on all fitted y-values, as indicated by the Cook's distance values being lower than the 20th percentile of Cook's distance. But the model does appear to have several outliers with respect to x, as indicated by the leverage values. Thus, the first remedy applied to the model was to remove the outliers on x. Removing the outliers slightly improved the adjusted R-squared, but did not impact the other violations. The best subset model was then determined based on the criteria of having the highest adjusted squared and lowest CP, AIC, SBC, and PRESS-P values. After running the best subset algorithm in R, it was determined that x3 and x5 can be dropped, leaving the best subset predictors to include x1, x2, and x4, which correspond to mass and size of area under study for the tumor and area of skin damage, respectively. From the preliminary analysis, we saw that there was high correlation among the predictors. So one way to account for the multicollinearity caused by highly correlated values is to add interaction terms. After analyzing the VIFs of the best subset model, it was determined that there was a major multicollinearity issue of x1 with both x2 and x4. Thus, the interaction terms for x1, x2, and x1, x4 were added. To address the non-constant variance and non-normality issues, a Box-Cox transformation on y was performed using a lambda value of 0.0909. A constant of 2 was also added to the original y value to ensure that all fitted values were above 0 for Box-Cox to work. Based on the analysis of the remediated model, the adjusted R-squared was increased slightly, but the Brown-Forsyth and Shapiro tests still indicate unequal variances and non-normality. Adding the interaction terms also added a multicollinearity issue for all predictors based on their VIF values. To address the unequal variance issue, weighted least squares regression was performed. 2 iterations of WLS had to be performed to stabilize the parameter estimates. In my analysis of the model after applying weighted least squares regression, I found that the adjusted R-squared increased significantly to 0.5355, which was almost double of what it was before. The unequal variance and non-normality issues remained as indicated by the Brown-Forsyth and Shapiro-Wilk tests. But looking at the residual plot and histogram of the residuals, it can be observed that the distribution of the residuals became less skewed and slightly more normal compared to the original model. So there was a noticeable improvement in the normality of the model. The multicollinearity issue also persisted as indicated by all VIF values being greater than 10. To address the multicollinearity issue, ridge regression was performed on the model. Based on the ridge trace plot, a biasing parameter k of 0.1 is where the coefficient estimates began to stabilize, and this coincides with the results comparing the VIF values at each k on the right. K equals 0.1 resulted in the VIFs for all variables to be relatively near 1, indicating that the multicollinearity issue was removed. Although higher k values had VIF values much closer to 1 for some predictors, they were not chosen because other predictors for those k values had VIFs lower than 1, which could indicate overcorrection of the model. K-fold cross-validation was then performed to validate the final model. 3 models were compared. The first one is without the interaction terms, the second one is with just one interaction term between x1 and x2, and the third model is a full final model. According to this cross-validation, the final model with all 5 predictor terms has the lowest root mean square and highest R-squared value, indicating that it is the best choice among the tested models. The final model attempted to address all issues present in the original model. Such issues included a low R-squared value, unequal variance, non-normality, multicollinearity, and outliers. The suggested final model removes all X outliers that were assessed based on the leverage values. The unequal variance and non-normality issues were addressed with the Box-Cox transformation on Y and weighted least squares regression. While these remediations improved the model, they did not remove these violations entirely. Multicollinearity was addressed with the addition of interaction terms and were then resolved using ridge regression. Using the final model, I addressed the research questions I stated earlier on in the presentation. Based on the added variable plots as well as the parameter estimates, it was determined that x1 and x2 had a positive impact on the response variable, given that all other predictors were present in the model, whereas x4 had a negative impact on y. As mentioned previously in the presentation, the best subset of predictors ended up being x1, x2, and x4. A GLT-F test was performed using the best subset model as the reduced model and the original model as the full model to confirm that x3 and x5 could be dropped. The third question about whether the final model still violates any linear regression assumptions was answered by the diagnostics performed on the final model, and as stated before, unequal variance and non-normality are still an issue, but were improved upon as shown by comparing the Brown-Forsyth and Shapiro test p-values, as well as the residual histograms of the original and final model shown on the right. In terms of the final question, the summary table of the final model shown on the bottom left contains the p-values for the t-tests of each predictor, which provides some indication of the impact each predictor has on the model. These t-tests evaluate the impact that dropping each predictor would have on the model. Based on the p-values, x4 has the lowest p-value of less than 2 to the negative 16th power, indicating that it has the most significant impact if dropped from the model. However, x1 and x2 also appear to have a significant impact on y based on their p-values. Considering that the final model was unable to resolve all issues of the original model, there are some limitations to the suggested model. For example, the sample size is relatively small when compared to the original dataset size of over 9,000 points. The use of MLR may also be less appropriate for predicting tumor size compared to the past machine learning methods used to approach this problem. For example, ensemble learning has the advantage of combining predictors from multiple models, rather than relying on one model to make predictions, which may increase accuracy of prediction performance. Like using transformations in linear regression, feature engineering can turn non-linear problems into linear ones. But it does have the advantage of being able to extract key features from the raw data more efficiently, which can optimize the data screening process prior to model building. Thus, to improve this study in the future, I could use a larger sample size to encompass the wide variety and different tumor attributes and try other regression models that could be better at addressing the non-linearity issues. Furthermore, I could also look at other tumor attributes such as tumor depth or add qualitative predictors like tumor color, which may also contribute to the prediction of tumor size and potential for growth. Thank you for listening to my presentation.